Hey there, welcome to Solve My Math Homework. We are the YouTube channel that only solves the math problems our subscribers send in. So we have another linear regression problem coming in today, and this one is fairly straightforward, but it asks us to do a bunch. So let's get into it. It says a company is tracking the number of times a post to a popular social internet site has been shared. That's a very weird way of saying it, but sure, it's a social media site, and they want to know how many times it's been shared in relation to how many hours the post has been up. So the data is shown below, and it says hours is our independent variable x, and the number of times shared is y. So we've got the data 128, 244, 349, 465, 588, and 6100. So the first thing it asks us to do is determine a linear regression model for this, okay? So that's going to be your linear regression. We're going to use the TI-84 to do that. Then we're going to do an exponential regression model. Again, we're going to let the calculator do all the heavy lifting on that. And we're going to round everything to the nearest 10th. I think I probably will round to the 100th, but whatever. Correlation coefficient for both models when rounded to the nearest 100th is r equals 0.99. So it gives it to you, and it wants to know what this tells you about the predictive ability of these models. Okay, so we could talk about that. Actually, we could answer that right now because correlation coefficient tells you specific information about how the data is related, but we'll get into that. So does your linear model from part A under or over predict the number of shares at 6 hours? And then it gives us some more data. It says after 24 hours, the post has been shared 10,952 times. Let me tell you, not once have I done a math problem that after 24 hours has been posted 10,952 times. I would be happy if it was shared 1,000 times. So this is some amazing post. Anyway, which model does a better job extrapolating the data out to 24 hours? So which model more accurately predicts the trend in data? Because when we do these models, we want them to be accurate. If they're not accurate, why the heck are we doing them? Okay, so the first thing you're going to do is get your TI-84 out, and you're going to go to Stat, Edit. And when you do that, you're going to go ahead and put your data into this list column right here, L1 and L2. I've already put the data in for this. Okay, so L1 are your X values. Let's just write this down. Okay, so you're going Stat, and then you're going Edit. And then L1, those are your X values. And L2 are your Y values. Okay, so I have put those in. Now, if you go from here to, if you go right from here, the problem doesn't ask for this, but if you go zoom 9 and then graph, you will see a scatter plot of this data. And I like to look at that just to see what I'm looking at. So when you do that, the data looks pretty linear, but remember, they have only given us very few data points. If we go back to the previous screen, they only gave us through 6 hours. So this isn't a lot. It kind of looks like it could start curving, but then this data piece does that. So, I mean, they've done a really good job of giving you limited data pieces so that you really can't say linear or exponential just yet. Okay, so now we're going to make our linear regression. Here's how we're going to do it. We are, once again, I'm going to highlight the things here. We're going to go again to Stat, and instead of Edit, we're going to go to Calculate right here, okay? And we are going to go down to Linear Regression, okay? This is what we want. We want number 4, Linear Regression. When you hit Enter, you're going to get this. You have to click down, use your down arrow till the Calculate is blinking. Once Calculate is blinking, you're going to go ahead and hit Enter, and it is going to give you your data. So ready? Let's see our data. Okay, now I am on the new TI-84 plus CE, which is supposed to be the newer grader model. The one thing I noticed, the first day I got this calculator, it no longer gives us R squared and R. I don't love it. So it only gives us this here. It used to say like R squared and R, oof, my handwriting is getting worse on this thing. Okay, so if you're using a TI-84 plus, TI-84 plus C, you likely see more data than I see here. Okay, so this is going to be our linear model, and it gives us the equation. A is our slope, okay, so this guy right here is slope, and B is our y-intercept. So our y-intercept is right here. So when we write this equation from this data, we say y equals 14.51x plus 11.53 repeating. And actually your teacher asked for tenth place, I did hundredths, so 14.5x plus 11.5. Okay, so that's your slope, that's your y-intercept. All right, so that was the first part of A. Then it said it wanted us to do an exponential regression. We're likely going to compare these two. Okay, so you're going to go back, clear this out, hit clear, and you're going to go back to Stat, Edit. Okay, and you're going to go to down, all the way down past 9 is 0, exponential regression. Okay, so once you click on exponential regression, it's going to look a lot like what we've done before. And here's our exponential regression data. Remember, your exponential functions are always in the form y equals a times b to the x power. Okay, where b is the rate. If this thing is more than 1, we have growth. If it's less than 1, we have decay. Again, a is given to us very clearly right here, and then our growth factor b is 1.28, so 1.3. So let's go ahead and fill in the information that this gives us. I'm so glad the TI does all the heavy lifting for us. So y equals, what's a? 23.8 times, and some people put b in a parentheses, it looks nicer, 1.3 raised to the x power. Remember, x in this case is going to be in terms of time. Some people put t. You don't have to. You can leave it x. All right? So let's go back up. We've done the first part of this problem. Let's make sure we haven't left anything out. All right? So we have a linear regression and an exponential regression model that best fit the data. In fact, let's go ahead and put them down now. Remember, we had y equals 14.5x plus 11.5, right? And then we had, I just did it, you think I would remember it. Let's change colors here. Then the exponential, we had y equals 23.8 times 1.3 to the x. So we have growth because our growth factor, our b, is more than 1. Okay, now it tells us a correlation coefficient for both models when rounded to the nearest hundredth is r equals 0.99. What does this tell you? Okay, well, we could have answered that at the very beginning. So r tells you, so the r value tells you that the data or the variables are correlated. They are related. So the variables are related. Okay, there is a relationship between the data. It tells you that a prediction can be made. So a regression model can be made that closely predicts the behavior of these two variables. That's all it tells you. A lot of people think that the R value means that it's linear and it's a strong linear model, but there are a lot of regression models. Okay, you can have a strong correlation coefficient, so a really high R number, and then find out that the data is curved. It's not linear at all. So what the R value tells you is that the variables are related. It doesn't tell you how. It's not the only thing to go by. You want to use things like residual plots, or at least looking at the data to go ahead and see if you have a curved regression or an exponential regression, and we're about to do that. All right, so part C says, does the linear model under or over predict the number of shares at 6 hours? So what does it do at 6 hours? 6 hours is 6/100. Okay, so let's get to a new page. So actual, let's put some ink here. Actual is 6/100. So the linear predicted, so predicted, but not predicted any. We want to say predicted linear because we did two models, would be that y equals 14.51 times 6 plus 11.53. Okay, and we did 14.5, so I'm going to do 14.5 times 6, which is 87. So y equals 87 plus 11.5. Again, I went to the 10th, but your teacher, or went to the 100th. Your teacher asked you to go to the 10th, so let's do what they said, right? All right, so plus 11.5, well, that's pretty easy. It's just 98.5. So our predicted is 98.5. Okay, what was our actual? Our actual was 100. Remember, our actual output right here was 100, predicted 98.5. So yeah, our linear underestimated, but not by much. So let's say that. Let's say that our linear model underpredicted. So our linear model underpredicted, okay? Because it did. And if you want to be accurate, say slightly. If they ask you to justify, you could say the actual was 6/100. The predicted was 698.5. Okay, pretty dang close for doing predictions with regression models. Okay, go back up to the problem because I don't know what the next problem says. Okay, so done here, done here. After 24 hours, the post has been shared again, a whopping 10,952 times. I think I would pass out if this post was ever shared that many times. And so it wants to know which model does a better job of predicting this. Okay, so let me get a blank board. So let's see. We have the point if after 24 hours, this post was shared 10,952 times, I think it said. 952. Then we want to know which one does a better job. The only way to do this is to plug 24 into both prediction models. So let's do that. And I think I already did this, but I did it for 14.51, so your answers might be slightly different if you do this just for 0.5, plus 11.53. So I'm going to go ahead and multiply 14.51 times 24 and add 11.53. Actually, let's just do it for the number you guys have to use, which is 14.5 times 24 is 348 plus 11.5 is 359.5. Well, that's not close at all. That is way off. And linear models will do that. Remember, exponential models start growing slowly and then they increase rapidly. So a linear model will look like it predicts something accurately for the first very small amount of numbers. The first 10, 20 numbers, the linear model looks great. But then after that, if it's truly exponential, the exponential model and the linear model will be far, far apart. Okay, so this is linear. And let's get to exponential. So let's get to a new page because it's driving me nuts. Okay, so remember we have 24, 10, 9, 5, 2. And our exponential model says 23.8 times 1.3 to the x power, and in this case, x is 24. So something very important to point out here. You have to do 1.3 raised to the 24th power first. You cannot multiply before you raise something to an exponent. That is a very common mistake that gets made in these problems. Please don't do that. So if we take 1.3 and we raise it to the 24th power, we get 542.8007. So then we will have 23.8 times 542, did I say 542? Yeah, 0.8007. So we're going to just multiply that by 23.8. And we are going to get 12,918, 12,918. So for sure, the exponential model comes much, much closer. It actually over predicts. Remember, because it was about 11,000 and this is giving us about 13,000. But remember what the linear model did. The linear model was so far short. Okay, and that's going to happen when you have exponential models. Linear will seem really good for those first 10 or so x values, and then exponential takes over because that's how exponential works. It grows much, much more rapidly. Okay, so let's see if we answered everything. All right. After 24 hours, the post has been shared a whopping 10,952 times. Which model does a better job? For sure, the exponential, because at exponential, we are at 12,900, and we were only like 359. I don't even remember. I should remember. So there is all your information. So for sure, this one is exponential for sure. And really, if you want to justify this, just show your work. Your work shows it. All right, that's it. I hope that helped. I know you have a test tomorrow, you said in your email. I hope this helps. I hope you ace it. If you're watching this and you didn't submit this, well, guess what? I only solved this because a subscriber sent it in. So if you're not subscribed, that doesn't make a lot of sense. Because if you were subscribed, you could send me your crappy homework problems and I would do those too. Thanks for watching. Have a good one, guys.